Okay, hello everybody, and welcome to meeting number 3 of Move the Bytes working group. Today is December 14th, 2022, and I'm excited to get in. Our agenda for today is nice and simple. We have 5 minutes of just quick housekeeping, and then Juan is going to give us a great talk about data transfer, discussing a number of things. This says open discussion 35 minutes. That's just going to be the remainder of time in the hour. But just to remind ourselves of why we're gathering this meeting or this group, we're trying to ship a data transfer protocol that can replace BitSwap in Q1 2023. I put an emphasis on can over the others because as I've been having a number of conversations with other folks as we talk about the purpose of this working group, I think the emphasis should be on the capability to replace, not necessarily that it is implemented in the wild. And I've heard a little bit of confusion of hey, is this working group intending to formally ship this in every implementation of IPFS ever by the end of March? I don't think that's plausible, but instead this is about actually coming up with a viable alternative to BitSwap as we move forward on a meaningful time frame. Speaking of timeframes, this is where we are. We're currently on meeting 3 of our meeting agenda of our schedule. We have our speaker for when we come back selected. Hannah Howard is going to be talking to us on January 4th. She has a proposal for a new data transfer protocol based on a lot of her research. Many of you may know Hannah from her work on GraphSync and a number of other data transfer protocols in our Merkle forest. So I'm very excited to hear Hannah sort of drop some new heat on a new data transfer protocol spec. So we'll be hearing about that in our first meeting back on January 4th. A couple of notable reading bits that have come in from the Move the Bytes working group channel. The effectiveness of BitSwap discovery process. I do want to call out this one. This is coming from the Probe Lab team. That is authored by Guy. This is RFM stands for Request for Measurements. So this is their 16th Request for Measurements report. It's a really in-depth report on BitSwap as a data discovery tool. I highly recommend others take a read through that. I think it's really worth taking some time to digest. Then moving right along. Today, metrics report number 3 was supposed to come out. We have no report this meeting. Mainly because we have to spend some time reevaluating the actual cost of putting these reports together. Behind the scenes, what's been happening as we've been putting these reports together is they've been really just-in-time compilation in the sense that we are running the measurements kind of the night before the meeting, posting our results. We've been getting a lot of feedback on both what should be measured and feedback from the team implementing the measurements that would benefit from at least a pattern of stepping back for one meeting to sort of clean up and polish so that we're not just kind of constantly hacking together results. And so for this meeting, we elected to at bare minimum step back from doing a report and instead spend some of that time cleaning up the infrastructure and pieces necessary to put together these reports. We think it's a small investment that'll yield better long-term results for this. We just have to figure out a way to sort of scale our measurement systems a little better. And so no report this meeting. We can talk about having one next meeting, but I think that's also a great launchpad into making sure that this working group is giving everybody and all stakeholders that are coming to these meetings what they need and what they want to get out of this working group. So what I'm proposing we do with that is I would like to solicit more feedback from the folks in the working group and around the working group. I've been talking to a number of you asynchronously, and I think this is a great time for us to have an asynchronous discussion in the Move the Bytes working group channel about what everybody wants to get out of this working group and make sure that we're aligning properly on that. At number 0, we are still very dedicated to shipping a viable data transfer protocol. We need one for sure. And I know a couple of other teams are aligned on that need, but we want to make sure that we're reporting out stuff that's useful and providing the proper on-ramps for folks to get something valuable out of this working group. And that rather than have that as a discussion sort of synchronously that may exclude folks who are on the call, I think it'd be best to structure that as a channel, as a discussion that I'll kick off in the Move the Bytes working group channel inside of the Filecoin Slack after this meeting. So look out for that. If you're looking to weigh in on what this working group is doing and its primary sort of reason for existence, that would be a great place. And we're really soliciting feedback on what is and isn't working for folks as we try to figure out new paths forward in data transfer. That's our short update for logistics and housekeeping this week. And with that, I wanted to save as much time as possible for Juan to give us a talk about data transfer, thoughts on data transfer. I know he's prepared a number of notes that I think are super informative for this group. And so with that, Juan, are you cool to take over?
Yep, thank you. 1 second, I'm gonna get stuff processed. Cool. Let me know if you can see that. Great, yep. Awesome. Great to see everybody. I'm really excited about this working group, and had a good time watching the last 2 talks. So a lot of what I'm going to say here is already in strong and violent agreement with many of the things talked about before, but also some. I do have like a few ideas that need to be kind of like revived a little bit, and some ideas that are probably pretty different from what other people are thinking about. So I wanted to kind of like start by both. Before I get to the ideas, I want to talk about 2 sets of things. One, a set of recommendations for the working group in general, just because I think there's a lot of people here that want to solve these problems and want to get to good solutions quickly. So I kind of want to talk a little bit about the meta there. Then I want to kind of stress the importance of an experimental setting, and I want to get a few concrete ideas here of like how you can kind of level up the measurement over time, and how we as a community can keep like improving this. So this is in a drastically better space than it was a year ago, 2 years ago, 3 years ago, and so on. So it's in a great improvement trajectory. However, there's probably a lot to be done there before this working group can like leverage a lot of the tooling. The last doing some like discussion about like latency, for example, as being like a gap and whatnot. And then after that, we'll go into a set of ideas. So one big kind of meta point here is like doing this together is drastically better than doing this alone. So as many of you can attest to, like this is a very large problem space with a very large possible potential design space for solutions. There's lots of different applications that have different requirements, and there's an enormous amount of stuff to instrument and test. And when you even if you have like a good solution that hits a set of applications, somebody's going to come along with new applications and new requirements and so on. And so things will have to keep evolving. So a kind of one of the pieces here is that as a community, we need to be able to keep experimenting with these different potential solutions for moving around objects. Sorry, somebody is unmuted. Somebody can mute that person. So think like getting to a spot where we can design like extremely good benchmarks and work for various different workloads, and we have a good way of getting reports out of those benchmarks for different kinds of protocols in different devices and whatnot. Like that's what the community is going to need longer term, more than a single protocol that's just gonna kind of solve a bunch of problems. What I'm trying to get at is like necessarily because of the very different kinds of applications and different kinds of networks, this will yield different style of protocols, and it's gonna need to keep evolving. And so having a kind of a strong emphasis towards measurement infrastructure from the community to be able to do all of this together is going to be super, super valuable longer term. So congrats on like setting up this working group, which is solid. B, as a community, we should like invest deeply in this working group now to level up our infrastructure and level up our measurement, level up all the tooling and so on, so that we can kind of get to better solutions. Great. So then from that, I wanted to kind of talk a little bit at the meta level about a few different things. So one is the application context really matters. Different kinds of applications are going to want to do different things, and many of the discussions that differ just come with different contexts. And so you're going to end up wanting different protocols because of that. Now, it is possible you could have like one protocol that handles all of that, but it's just beware the complexity that protocol might assume. And just know that like a lot of the constraints will differ for how you move around data. So in some settings, you're trying to just replicate some large file or large set of files and whatnot, and like that's a much more straightforward thing. In other settings, you're trying to get a large set of peers to pull subgraphs from each other, and so on. In some settings, you're trying to push. You're not even pulling. You're like trying to push content to other nodes and whatnot. So the request reply latency problem kind of changes entirely. So just recall the application context really matters, and you want to have to the extent that you can make this application friendly, the better it'll go. Meaning, if the application can choose something and tune something for its use, like that'll be great. Now, the problem with that is maybe I'll skip for a moment before talking about thread models. The problem with that is you can end up writing too many protocols that then have to be written in too many languages. And like we already have this now. So when we started GraphSync, the goal was to replace BitSwap. So the idea was like, say, hey, let's take everything that we know from BitSwap, write it into GraphSync, and replace what we had before based on our learnings. And the idea there is like, hey, we're no longer swapping bits, we're swapping graphs. Let's, and hey, it's not, now we're really kind of like want a sync protocol as opposed to just kind of an exchange protocol and so on. So that's why it evolved in that direction. However, at the same time as some of us were working on GraphSync and building it, other folks were working on evolving BitSwap with like all the BitSwap sessions and whatnot. And so we ended up with like now 2 protocols and a variety of implementations and clients across a variety of languages that now, you know, like don't speak to each other. And there's so many like groups trying to put in BitSwap and or GraphSync into more components. So having many protocols can be super painful. So there's kind of like a warning against that. On the other direction, beware one protocol, because you can also end up in a spot where like, hey, it actually just doesn't work for everything. Even something like Git has multiple protocols. Now, the way it works and why Git manages to succeed with having multiple protocols is because it sort of enforces that all Git clients are going to implement all of those protocols. And I think if there's 2 or 3, and there's like some experiments that like add more and so on, but none of them have quite succeeded in those 2 or 3. And so the point here being, if we end up in a world where there's many protocols, then we're going to have to figure out how to like make sure that everyone speaks to each other. This is another plug for programmability. So things like MTGWG and so on could really help here when, hey, loading up a new protocol, it's just downloading a WASM module and running it. Like maybe you're in a good spot. But then at that point, we're going to have to solve the, you know, who gets to decide what these transfer protocols do and who gets to publish them and so on. We could get to a good spot there by like just writing these protocols in WASM and having a community-oriented process for deciding which ones of these are like good and like, you know, relatively bug-free and whatnot. But getting into a spot where you're fetching the protocol at runtime from a dynamic source and so on without any kind of certainty, like opens up a ton of like potential for attack, right? And so from a security perspective. So I would say like there's significant benefit to programmability here into getting us into a spot where we can experiment with different styles of protocols to get them to work for different kinds of applications. But if we do that, we should A, really lean into WASM and IPVM and all the IPVM work that we're going to be doing there. And B, figure out a community process by which we like sort of bless a set of protocols to be safe to like load up at runtime. We don't want to be in a spot where like you're kind of allowing anybody to write these. And even then, just be aware of kind of the explosion of possibilities there. Like you know, there's lots of good examples in history of certain kinds of exploits enabled. Like I think like Java had a famous one where like, or no, XML had a famous one where like you like some expression would like enable you to, if you wrote the expression just right, you could like blow up the cache of the local machine and so on. So the point being, I don't think we can get to a single protocol that's going to work for everything with the perfect setting, and I don't think people will be happy. However, getting to a world of too many protocols, even just 2, is too much in a sense. Like we already two protocols with many possible languages and places to implement is already kind of a nightmare. And so we either have one protocol or we invest in programmability, I think is kind of the output of that. So that may not kind of change this working group's in immediate work in a sense, in that like, hey, you're kind of trying to experiment and find a better protocol for now. And that's all good, or improve the current ones, and that's great. But it might change your like mid to long-term goal set, in that what you should be doing is probably writing in Rust and probably targeting WASM, and kind of a lot of other protocols in other languages that probably don't make a lot of sense anymore. That would be my guess. The other thing here that I had around thread models, the sync protocol changes a lot if you're dealing with trusted nodes or totally untrusted malicious nodes that might be changing their software to try and mess you up. So different kinds of protocols might evolve with different capabilities. So and here I mean capability, crypto capability. So if you show up with like the right capability, then you're kind of in a trusted setting, and you get to be able to, you can trust like the other side much more. If you don't have that and you want to be kind of in the Bitfields model where like you don't trust anything, then you have to be a lot more conservative, and you maybe don't trust the other side as much. Just kind of factor that in and keep it in mind as you design things. Talking about experimental settings for a moment, just remember that like you only improve what you measure. So as a community, we will only improve the stuff if we have good and reliable and robust measurements across all the areas that we care about. If we don't measure it and we don't keep measuring it, it'll either not get fixed or degrade over time. Like you might spend a lot of time measuring something and fixing it, you get it into place, you stop measuring, software evolves, software rots, something changes at some point, and that's suddenly things are slow again. So the only way to get things good is to establish a really strong experimental loop and keep running it, meaning getting it to CI and keep testing things at scale. Just as in terms of an experimental loop, like you have to, of course, software is going to keep evolving, which means, and in addition to keep evolving, because the problem space and the design space is going to keep evolving too, the velocity of a community writing software is much more important than its position, meaning the ability for a community to change the software and adapt to the changing environment is going to outweigh however good it is at any one point in time. So like, even in our community within IPFS, I've had so many conversations with people who are like, oh, great, like, let's not invest in all this like testing. Let's kind of write a great protocol once and like, we'll improve it and like, then it'll be solved. And this, the story of like BitSwap a few times over, where a lot of work went into improving BitSwap to a certain point. And if we had invested that time into the testing, maybe things would be in a much better spot. And just kind of remember, like, we're going to be rerunning experiments. So try to make them general so that you can swap out like the different underlying transfer protocols. So let's talk about testbeds for a moment. One thing I want to, so I'm going to talk about like some industry examples. I want to talk about TestGround briefly, the IPFS Observatory, and then some other things that might be in the pipeline. So the kind of the great software that we use and rely on day to day to do most of our work is tested massively at huge scales. So this goes into even things like programming languages, things like Go and Rust and so on have pretty serious benchmarks for every single commit that happens. Browsers very famously enable thousands of people to contribute to the thing, and they keep that working well and they keep performance high because they have invested in massive scale testing across tons of different machines. They have super insane workloads to test all kinds of corner and edge cases to be able to know as developers that when they contribute one change, that change is not destroying performance in some way, or ideally is improving performance. And they put a very strong emphasis on the kinds of things that improve performance. Kind of famously, like Chrome for a while, I don't know if this still exists, but Chrome for a while had this like, top 10 improvements in the last 7 days for perf and top 10 regressions for perf. And so right away, if you wrote this commit, you could know that like, oh, wow, like my commit just like blew up performance. Like that's bad. Like that's clearly not going to stay in. Or if you greatly improve performance, then you got a ton of credit in that community. So the point being like, we can use the CI structure and the testing structure and the benchmarking and the metrics and so on to drive a lot of improvement as a community. But it sort of requires that kind of investing in that experimental setup in a sense. And are in a much better place today than we were in the past. But we're still kind of working towards that. So TestGround exists, and a lot of folks have been using TestGround. There's still a set of features that are missing. We should kind of work on closing those out, and we should think of like how to make it more repeatable, more useful, like potentially generate reports for us and whatnot. Like getting to a spot where like you can write a new protocol and add it to a suite of tests and just get out a bunch of reports that show like how it stacks up, or like you try a branch, you try some experiment, you try changing something, and you see like how that compares against like the standard version or other protocols. Like that would be the ideal place to be. And this call opened up with Brendan saying, hey, like, hold up, we're not going to have measurements today because like there's a lot of work to do. And like that's precisely the point. It's like we as a community need to solve that problem, and there's a bunch of stuff that we need to do to enable that so that it is not expensive. Like if imagine the setting, and imagine that like you're going to make a commit to Chrome, but in order to make a commit to Chrome, you have to like run experiments yourself and argue that this is actually going to be better and so on, and like present the data and whatnot. Like it's just going to be kind of intractable and impossible to do. Like we have to get to a point where like this just all runs automatically in the background. Like you make a change, you push it somewhere, and like CI produces all these reports out for you. And so I would kind of encourage us as a community to invest in that part. I want to, huge plug for like the work that ProLab has been doing, measuring a lot of things and creating like really good reports. It's been kind of leveling up at a lot of the conversation. And even in the last two calls in this working group, we saw a bunch of the there's several graphs from this group where you used to kind of like motivate decision making. So that's great and working really well. It'd be great to get more ProLab folks in this working group working with you to help design some of the experiments and help design some of the infrastructure to keep testing the stuff or the graphs. Sometimes like a well-designed figure can make a huge difference in guiding a process, right? So a design or an engineering process. So getting the folks involved might be helpful. So something to keep an eye out for is we're likely going to be in a spot to be able to run experiments with thousands of machines and later on tens of thousands of machines later this year. And next year, I think we can probably hit millions. So one really neat thing is that now we're going to get to a spot where we can run massive test cases across these networks. So we're doing the work today to enable users with access to servers, desktops, or phones to be able to run arbitrary like computer over data networks and things like that. Then after that, we need to write tooling to be able to issue kind of tests across these things. So when you sort of like put these things together, like imagine being able to run TestGround or a related type of thing over a network like this, so then be able to test certain workloads at massive scale. So we have some goal to like we have like some protocol that is supposed to work in a particular way. Okay, great, like we can test it now. And this is the sort of thing that will enable us to test not just kind of the immediate things about changing a protocol, but like it might address a bunch of the questions people have about multi-peer downloads or how these protocols work with content routing. So how this kind of works with DHCs or indexers or whatever, and how those performance metrics totally change when the workload is working a particular way. But anyway, just kind of like this is out of scope for now for the working group, but like this will become like more relevant later in the year and next year. One other thing I wanted to kind of flag is great file systems and great distributed systems have relied on extremely well specified workloads. So that means it is worth spending some time figuring out precisely what are the workloads that you're trying to optimize for, and create those as like create a repo somewhere that like where you can add new workloads. And so new people, as soon as they want to optimize for something differently, they write up a new workload and they add it to that setting, and you can then test out the performance of moving around these kinds of workloads. So because you'll have differences, like workloads where you're moving around one big file will look very different than moving around like subsets of like little pieces of a file, or that'll look different than video, and that'll look different than database, and that'll look different like than a WinFS graph, and so on. So getting ahead of this and like figuring out what the workloads that you want to improve are is going to be time well spent. Now, it might not be worth doing now. At least some of the graphs that I saw in the last couple of talks showed that like there's just a lot of low-hanging fruit in just getting some of the basics done first. But this, I think, pretty quickly is gonna make a huge difference between, in factors like 2 to 10 in terms of how one protocol works relative to another. So figuring out those workloads will matter. And then, of course, reporting, right? So with any of this kind of experimentation, getting to making sure the data is accessible, the takeaways are clear for everybody, good figures, write up things, present it and whatnot. Like this is, standard experimental loop type of thing. Now, ideally, like this is, hooked up to CI directly, so that again we can get the kind of setting like Chrome and Firefox and so on, where like you're making a change you're experimenting with something. You can push it to a repo. You can get like a whole, easy report that shows you like how this thing performed relative to others. Cool. Now, with that, I want to jump to some ideas. So I piled up a set of ideas here, and there's probably others that'll come to mind as I go. But I want to talk about kind of some insights from the HTTP model first. I want to talk about like new connections and why they really hurt. So this might be less relevant to this group, but I think it should kind of give you pause when you think about multi-peer. So meaning like there's a number of folks that have been pushing really strongly for like single peer retrievals and so on, like that. All that makes sense. Just kind of, I want to flag like that new connections can hurt a lot. I want to highlight Bitter and Bitfields. So it's great to see Kraken Sync using Bitfields as well in the last one. Like that's great. This is one of the ideas that very early on I wanted to implement in BitSwap. It just kind of time passed and we never got to it. And when we built the graph sync, we thought about doing. I want to talk a little bit about pipelining, structured traversals, and why they'll matter for a bunch of applications. I want to talk a little bit about 2-hop requests. I want to talk about how Git does it, and then maybe discuss certain things about both encoding the data and keeping metadata that might really help transfer protocols. Cool. So I don't have slides for all of these, so I'll just kind of, for some of these, I'll just talk through while looking at this slide. So in the HTTP model, first and foremost, we have to remember that like the HTTP stack has been hyper optimized by thousands of people to serve a lot of data really quickly to tons of applications around the world. So HTTP stacks have been hyper optimized already. So, and much more today than even when IPFS started. So when IPFS started, HTTP was not nearly as high performance as it is today. So in the span of time that we've been building IPFS, the HTTP world has greatly improved in its own stack. We've gotten things like HTTP 2 and 3. We've got the TLS model evolved. We have just a ton of like better tools for distributing HTTP content and so on. So like an initial plug that I would have for everybody here is that one potentially great hack might be just leverage the HTTP stack that has been hyper optimized for request response for data and write a very lightweight kind of graph sync style protocol on top of HTTP. So that means provide like requesting and serving a CID as like one of the path parameters, and potentially a whole car file or a whole graph or whatever, and just ship that as like a super basic request reply transfer protocol on top of HTTP, and leverage the fact that a bunch of HTTP stacks have been hyper optimized underneath the hood to deal with tons of requests at the same time. Being able to handle millions of requests is like a standard thing for a good HTTP stack. Being able to do kind of request pipelining, all of this kind of stuff is already built into them. So a very, very great, a cool hack that this group might come out with is just say, hey, guess what? Like just put HTTP into IPFS and just lean on all of those solutions. We don't have to kind of just do things from scratch, especially since they've been hyper optimized since then. Cool. So on new connections, I want to kind of make the point to this group. So like new connections can be super damaging. And the reason is, and this is one of the pain points of peer-to-peer in general, and one of the reasons I don't think DHCs are that good in general. But it's not just speed of light. It's how speed of light hurts you when you're setting up new connections to new peers, given the security context that we're in. The security context that we're in usually requires establishing an encrypted communication channel between new peers, which usually means multiple round trips. Sometimes one, sometimes two, but usually more. In this particular diagram that I have here, this is like from 2019 when we had like much worse handshakes and multi-stream was like slower or whatever. So we ended up with like 4 to 6 round trips to set up a new connection. And this shows just how slow a DHT query was at the time. Like this is a trace of the graph on the right is a trace of a DHT connection. There's a request. Each row is a different peer that I'm trying to connect to. The length of the green bar is the length of like from the moment when I first send the request to them and I start trying to open a connection to when I start I get a response from them. And some of these bars were like we can't quite see the time here, but like some of these bars, the bulk of them are kind of like 4 to 5 seconds long. And so when you're kind of limiting the number of like active requests that you have going and so on, and you're trying to talk to this many parties, you spend most of the time either in these kind of like round trips to establish a secure channel and waiting to get the answer from the party that like sorry, the princess is in another castle, right? Like the thing you're looking for is not here, go look somewhere else. And so these kind of like peer-to-peer protocols where you have to open tons of new connections to new peers that you've never seen before, or that you haven't seen in a while, and therefore you don't have their keys and you don't have an encrypted channel, like really, really, really suck. Now, caveat here could be that you could get around this by deploying things unencrypted, which that was David Mazier's suggestion in the Fireside and IPFS camp was like, no, don't encrypt that. It's like I personally don't think it's a good idea because then all of your requests are kind of going in the clear. So the other option is find an encryption model that doesn't lean on that. Potentially a DHT type request response protocol could be built to use public keys directly as opposed to trying to use public keys to establish a shared private key. Public key crypto is now, computers have gotten a lot better now than 20 years ago. So you could actually just use the public keys directly and encrypt the stuff. So you could have a one round trip type thing with request reply protocols to make something like this drastically faster. But this kind of like new ground, new cryptography and whatnot. This is much more important for things, again, like DHTs and so on, but it does kind of impact the multi-peer question for these sort of protocols, right? So if you're in the kind of like Bitfields versus GraphSync debate of having like multi-peer retrieval versus single peer and whatnot, people have pointed out there's a bunch of good data that shows usually you're just requesting for one peer, so single peer just optimize for that. But B, the point I'm making here is just multi-peer sucks because you have to you have to open up a ton of new connections, and that's really, really, really painful. And so you may want to kind of for the most part, you're going to end up always requesting from one peer, even when you try to request from many peers. Even if you're trying to request from many peers, unless you have stable connections or their keys, if you're dealing with very large networks with like tens of thousands to millions of peers, you're going to end up having to set up new connections, new channels and whatnot, and you're going to pay a lot in latency here. Now, this another heavy caveat to this entire diatribe is that this is for retrieving lots of small content from lots of different peers in a different kind of application setting where you're retrieving from a smaller set of peers or you're retrieving very large content, then this latency doesn't matter because spending even 5 seconds to start moving a terabyte file doesn't matter, right? And so this goes back to the points I was making earlier that like the application context will change the thinking. Cool. So I'm gonna go into Bitfields for a moment. So Bitfields are a great idea that should be used way more in these protocols. So it's great to see Craig and Singh talk about it last time. I'll mention it here again, and I'll kind of credit BitTorrent because BitTorrent is kind of one of the first protocols that leverage Bitfields this way. There's been a ton of other protocols, of course, over the last 20, 30 years that have used them in tons of different ways. But the basic kind of idea here is if you know the data that you're dealing with, if you can enumerate the objects in a stable way, then you can use Bitfields to communicate with each other terms of which objects you need and which ones you already have or you don't want, right? And so for things like BitSwap and others, like the want lists and whatnot, instead of sending entire CIDs, you're just sending a single bit per CID. Now you have to understand which CID you're talking about, and this gets difficult with dynamic content. The reason, say, BitTorrent could do this is because they did a bunch of pre-processing on an individual torrent. You know exactly how many pieces you had, so you could talk about each piece, and you could send easily as a Bitfield because everybody knew which pieces you were talking about. So you could easily refer to the 100th piece or the 201st piece, and both parties knew precisely what piece that was. Now in Kraken Sync, we're dealing with kind of a penalty log. I think the inspiration was kind of looking at a penalty logs from Hypercore and others where you already know the graph ahead of time, so you can kind of lean on that, and you can talk about Bitfields with respect to that graph. The same thing happens with graph sync. So one of the goals that we wanted to have is eventually have a selector that's a Bitfield selector over graph sync. So you could send around a Bitfield to select from a CID. So like you pass a CID and a Bitfield on top of that CID, and that gives you all the information you need to traverse the graph. Now, just one caveat, this is where thread models matter. So in a trusted setting, that's fine. In an untrusted setting, that could be potentially messy because you might not have the Bitfield might not actually match the real graph. So just kind of be aware that like these kinds of protocols work when you don't have like malicious code that is trying to exploit the fact that like how the Bitfields work and whatnot, or we might need to put some work in. If we wanted to work in malicious environments, then we need to kind of make them potentially have proofs and so on. Like this is one of the settings where like you could do some work ahead of time, pre-process some content, end up with like the shape of the graph in a well-described way and a proof about that. So you can say, here's a CID, here's the shape of that graph, and here's a proof that computation was done correctly. So now everybody can use that. The problem though is like, I would sort of like say like these are good, interesting solutions in the long term if the problem does arise, there are malicious nodes that are exploiting this Bitfield stuff. And this is not just kind of random speculation. This was an issue in some of the BitTorrent clients. So there were a family of BitTorrent clients that were altered to be malicious in ways or be extracted from other nodes, like things like BitThief and BitTyrant and others and whatnot. And those were examples where like they were manipulating kind of the exchange protocols and whatnot. So this kind of stuff can and will happen. Now, most of this group probably doesn't care about that setting. Most of this group probably just cares about, hey, let's just focus on, in a fully trusted setting, move around just bytes from one place to another, and like let's focus on making this fast. And in those settings, then yeah, just coupling having a Bitfield and being able to express Bitfields coupled with CIDs will work super well. Just be careful that once you kind of deploy that into the wild and you have random peers being able to request that, just make sure that you don't. Just make sure that you're not like your implementation is not exploitable if somebody sends you the wrong Bitfield. So just assume that whatever people send you, the Bitfield might be suspect. So as you write your implementation, don't like assume that that's correct. Cool. And yeah, I think there was a discussion in the last talk about run length encoding, which is it's why you can afford to generate like these massive Bitfields and send them around in a super compressed way. So like your one list can be tiny. There's a possibility here where even for very large graphs with millions of objects, we can really lean on this sort of direction to send around fairly large Bitfields, but might be worth to kind of move around. So as an example, like indexers and so on could be communicating with these kinds of Bitfields. Falcon SPs, for example, that host like massive amounts of graph data, could be communicating with these kinds of Bitfields. And so we can get to a spot where like you can precisely know what ranges of like what shapes of graphs are where and how to get them and whatnot. So I think some work probably should be done there to like figure out ways of leveraging Bitfields like that in those kinds of settings where you have multiple different independent graphs, and then you're starting to kind of bundle them together. And so you might be you might be trying to request things, or like you don't even have the CID of the thing that you're trying to look for, but you know how to sort of get it. This starts getting into pipelining where you're trying to send a random description of the thing that you're trying to request, so that the server kind of processes that description, resolves the CID that you're trying to get a thing, and then you on your side need to have some other way of like proving that that's like the correct thing. But anyways, kind of getting like more speculative. Yeah, so on pipelining, this was kind of the key design decision to make GraphSync, which was, instead of kind of doing this bit swap style thing where you're requesting layer by layer, you want to be able to pipeline and immediately request further down in the graph. So that could be like requesting a full path, or requesting down a specific, like down to like the specific shape of the graph. There is a problem here around codecs and being able to process the IPLD object that you get and being able to explore it. So yeah, I think this was already discussed last time around pipelining does not work well, or you can't count on pipelining if you don't know how to traverse the graphs themselves. My prediction is that this will be sorted out with WASM. So once we have IPVM and we have WASM, we'll be in a drastically better spot, and this pipeline will be back to working. And I think in the meantime, you can just kind of implement pipelining for a key set of objects that you care about, and or suggest that people like encode their things to CBOR IPLD, right? So if your other more advanced IPLD data structure encodes down to CBOR IPLD, then it'll just sort of work, and you can do pipelining and GraphSync on top of that. And so I think enough users will want to do that. That just supporting pipelining for those types of objects will be good enough. One constraint here around selector expression and evaluation is that a lot of very interesting selectors people might want to do get expensive to compute. However, the very basic ones don't, which means that you don't have to have a full selector super expensive evaluator thing and still get most of the way there. So you can kind of apply you can have something like close to full selector traversal that just supports kind of a smaller or dumber set or whatever, and get most of the utility and most of the benefit of selector traversals. So and on the flip side, on the other side, CSS is a great example of we can actually implement these kinds of things and make them really fast. So when you load a web page, your browser is doing tons of the kinds of set operations and intersections and traversals that a GraphSync selector or an IPLD selector would want to do, and your browser does them extremely fast, extremely fast. So I just wouldn't take for an answer that selectors are slow in general, because your browser does stuff like really quickly. Again, latency is the biggest problem. Like, you don't want to have to deal with the speed of light. Local computation can be massively accelerated. So I would just imagine that there will be a set of applications where selectors are just like super useful, and having a transport that enables that and just really doesn't kind of be around the bush there, and like really does support it and supports it really fast, like meaning the implementation has been optimized to support that. That'll, I think, in the long term end up winning, because you should sort of assume that in a few years from now, a lot of this stuff is going to be hyper programmable. Like you're going to have VMs everywhere. You're going to have WASM payloads everywhere. You're going to have machine learning models generating code, machine learning models generating new programs and new applications, and a lot of this sort of stuff is going to really rely on kind of local evaluation of whatever matters in that setting. And so I think like just assume that the world is going to get drastically more programmable, and smaller little embedded languages will be everywhere. And so these kinds of selector traversals will probably be the way that it'll work in the future. Now, it might not work there that way in the meantime, but up to you to decide. Cool. I want to talk about two-hop requests for a moment. So a lot of the graphs about the network today and the size of the network at the moment sort of point out that you could do some of these transport protocols and have them be two-hop instead of one-hop, meaning if you have a setting kind of like BitSwap where you send a one out, you could propagate it to a second hop, and that way greatly increase the likelihood that you're going to get the content back. So this is less about moving the data quickly, which is kind of what this workgroup cares more about. It's more about content routing and content discovery. However, it's worth mentioning here, because if you end up producing an exchange protocol that doesn't support this kind of thing and only lives in a single request reply world, in kind of like the traditional HTTP world, then you might kind of like make it harder to leverage these kinds of optimizations. So just kind of something to be aware of, in that, like, for the most part, you will be requesting everything from a single peer. However, you'll be finding things from many peers. And so just think of like the multi-peer setting is more about like content discovery than it is about downloading a lot of data from multiple peers. One plug for Git that I'll have here is like Git went through the very similar kind of discovery process as we are, and they ended up making almost the same kind of decision. So one part is they had a very simple and straightforward single object transfer protocol, where like you would kind of tell the server what you're looking for and what you have already roughly. Then you would make kind of like a dumb but kind of educated guess about what to send over, and then the server would just start sending you over a ton of little objects, and you can check them locally because you have to hash and so on. So think of that as kind of like graph sync. It was like a very special case graph sync sort of thing. You're telling like it what head you want, what head you have, what ref you want, what ref you have, and the server kind of figures out the difference between those two, figures out all the objects that you're likely missing, and then sends them to you. In order to do this, I don't know if the dump protocol does this, but it is likely that you have to send a bunch of your refs over, not just like the single head that you have, but you might to optimize this to reduce the likelihood for duplication and so on. Then you send all of the current heads that you have. The server looks at those, figures out what you're trying to get, and then just only sends you the objects that you don't currently have. And that's a really good, like pretty efficient way that a lot of data gets moved around. But now even there, Git found that this was too slow in certain settings, and that's where dealing with kind of like each individual object kind of sucks. And so this is where pack files came from, in the same way that we have car files. So we went through exactly the same discovery in a sense. Git ended up creating pack files and then moves around entire pack files as a whole. These kind of like bundles, large bundles of objects, and then you can move around, you can pull objects out of pack files. And pack files themselves also use delta compression, which is pretty sweet, because then you can kind of move around objects that way. There's a lot of stuff like well documented here for Git, so I'll just point you to that stuff. Maybe two final thoughts around encoding and metadata. On encoding, if you can change the encoder, and meaning how you like sort of shape the data and how you lay out the data, that could greatly change the speed too. So for example, BitSwap doesn't do very well with the default setting of graphs, which is kind of like this large balanced tree, because every layer is kind of expensive. If you instead like use like the left leaning, leaning trees where you can get to the data that you care about like really fast, then BitSwap actually can perform really well, because even though it's kind of layered and pipeline and so on, you will immediately get some of the objects that you care about, and you start being able to stream those out to the user. So in a video setting, for example, like you can get good video performance that way. The other thing around metadata, this is where kind of like decorating the graph itself with the things like the shape of the graph, the number of the objects, the size of the objects, all of that kind of information. If we as we were traversing the graph could know that information was there, then that could like yield drastically better distribution protocols, like drastically better replication protocols that could lean on that information that's in the graph. Now you have to worry about the graph being malformed and leading to security problems and so on. And so you have to be careful. But that could be like a drastically better place to be. So I would encourage this group to not just explore ways of just moving graphs, but also how to encode data to make the movement of the graphs themselves like way, way better and way faster. Going back to like the Bitfields, for example, you could decorate. If you were able to decorate the graph itself with like the shape of each node could have a shape of itself, then the Bitfields could work extremely well, and you could use the Bitfields to like figure out what's underneath a particular CID and whatnot. But again, we'd have to like either trust the data or have some proof that that encoding was done correctly. Cool. I'm gonna stop now because I want to leave you at least a few minutes for questions. But great talking.
Thank you so much, Juan. Does anybody have any questions? We can use the. Do you want to kill screen share, Juan, for a sec, or what are you thinking? Perfect. Who's got thoughts? Who's got questions?
I'll catch up with the chat.
Yes, there's a lot to read on there, but I think one that I would that jumped out to me that this group has really been struggling with is the interplay between content discovery and data transfer, right? And specifically that we have, one of the first questions that came to the working group was like, BitSwap does a whole lot of content discovery. What are the responsibilities of that? And particularly when we think about Kubo, like there's a tight coupling there. And there's, as you mentioned with the 2-hop request conversation, there's also like, what are we putting in DHTs and network indexers? Are we just putting root CIDs, or are we just putting like, are we putting root CID plus Bitfield? Like, and so do you have a cut on how we should be trying to pull those things apart?
I guess two ranges of thoughts. On the discovery protocol side of things, I do think that in tons of applications, many developers will like want to leverage the optimization that if you're already connecting to a set of peers, you should be able to pull their data from them, or you should be able to kind of like ask them for the content just in case they have it and whatnot. And like that's a very cheap thing to do that can optimize bandwidth and use and all that kind of stuff. So I think like that's the case. And so, but it doesn't mean that a single like a single party or like two-party protocol could be wrapped by a multi-peer protocol, right? So you could have like a single peer retrieval thing that gets wrapped by another thing that like is the one that kind of knows that there are many parties and many peers, and you may want to send requests to multiple of them and whatnot. This would be a way to sort of like put it in concrete terms would be say, take like the BitSwap sessions component and then abstract it to be able to plug in GraphSync and other kinds of things within that. The other side in terms of the proofs and whatnot, my sense is that computing proofs over code is going to get cheaper and cheaper and cheaper and just much more prevalent over time. And it's just that it's right now is very clunky and cumbersome. And so I probably wouldn't recommend anyone worry too much about it at the moment or spend a lot of time on it now. But I do think that eventually it'll, this will sort of become the norm in a lot of software. Like you'll be able to carry around proofs that the software is like doing things correctly. We're probably about like 3 to 4 years away from that being super cheap to compute. And then after that, like people will just start embedding this in a lot more places.
Juan, I really like your point about the whole question around one protocol versus many protocols, and the fact that like there are the set of use cases is really large. This group has already been struggling with that, and I feel like when you start with like replace protocol for everyone, like you immediately have like a general case set of use cases you have to satisfy that makes it very hard to even build anything from get off the ground. So it's interesting. If I was hearing you right, you were sort of suggesting that we possibly abandon the idea of one protocol, which I think is right, and then hopefully solve the problem of protocol proliferation with programmability eventually. Though that does seem itself to be its own sort of like, let's hope this all lands and works, you know. But I like the end. But your suggestion is write it in Rust so it's at least compilable to WASM, and then when all that stuff is there, maybe that'll be not a good transition. If I understood your like for now suggestion.
Yeah, that's exactly right. So what I would do is like, I would not try to shoehorn every single use case into one protocol. I would be okay with having a few, and then I would use programmability to get out of having to implement it everywhere. And I would and I've said this like in other places, like if I was designing IPFS today, I would, or two things. One, if I definitely regret not putting a VM in IPFS from day one. So meaning like having a VM in all IPFS nodes as soon as we can will be great. And then you can have programmability. There are ways of handling the sandboxing and ways of handling like the how do you trust the code that you're gonna execute and whatnot, or how do you keep those runtimes low and whatnot. And then second, if I were implementing IPFS today, I would probably implement most of it in Rust to then be able to just compile it down to WASM and run it everywhere, especially in like super small embedded devices that are just going to have like not going to be able to deal with like the Go runtime or JavaScript runtime and whatnot. So I would be okay with 2 or 3 protocols, write them in Rust, and plan to compile them into WASM and put WASM everywhere.
Yeah. I mean, also like that particular use case is one where like the proliferation of protocols is only hopefully n equals 5 or less. And so like, so then like that's relatively trusted, you if you have 5 well-known SIDs for the code to run those protocols, that's maybe not as hard as some of the other potential, things that could happen. Cool. That's all.
Fantastic. I think we have time for one more question. It was a great question. Does anyone have percolating thoughts that we haven't heard from? Going once, going twice. Okay, well, I do think that is a phenomenal takeaway. Thank you very much, Juan, for coming to talk. I think it was a great kickoff for how we're going to modulate this group's purpose moving forward.
Great. Thank you so much, everybody. Great talking. And thanks for doing this super valuable, important work. And let me know if I can be helpful along the way. All right. See you.
Thanks a lot. Have a great one, everybody. We'll see you in the new year.